To talk about gravity and non-equilibrium thermodynamics and how these two things might be related. This is work done with the Japanese student Yuki Yokokura. It doesn't work.
You will switch. You have to press something and on the keyboard.
On the keyboard, which?
Is below.
Which one? Oh, here.
Just press one any button.
Any button, and then that work. Sorry. Oh, this one doesn't work. No?
No, you won't want to switch.
How do I go back? Oh, I really need to stay here and shoot. I cannot control it.
No, you need to.
Okay, okay. So let's start by, Bronstein was the first worker in quantum gravity and invented this theory, Bronstein cube, which essentially explored the sets of possible physical theory based on what dimension full parameter you turn on, either G or C or H bar. And what we're looking for when we think about quantum gravity is somehow being in this corner where they all turn on. Whereas when you think about thermodynamics is really down this corner there. You know, they're all turned off. It's a classical theory. So it's kind of surprising to imagine that they would have any connection because they're really, at opposite ends of this Bronstein cube. Oh, that's going to be annoying. Okay, so now there seems to be lots of evidence between a correspondence between black hole in the literature and black hole physics and thermodynamics. And the question I want to investigate here is whether this is just an analogy, or there is somehow a deeper correspondence behind that thing. And I want here to argue in favor of a deeper correspondence that not only is valid for equilibrium thermodynamics, which I call thermostatics, but really extend to non-equilibrium thermodynamics. This is where thermodynamics takes its full expression. It's when you go to non-equilibrium. If you have such a correspondence, it can provide a beautiful point of view on gravity, which is fundamentally holographic, as I'm going to say. It can give clues on quantum gravity constituent, because if classical gravity is thermodynamics, I'm going to talk only about classical gravity, maybe quantum gravity is some kind of quantum statistics. And it also allows to do experiment in the labs. That is the physics of, you have an expert here, but I'm thinking about other type of experiment that people do in soft matter physics, which would be classical gravity experiment. So what about black hole, and what's the fascination of black hole? Let me just review a few things about black hole. Is that the way we form a black hole is by taking two massive objects and collapsing them onto each other. And usually this collapsing phase there's different phases to the collapsing phase. There's an orbital decay where the two objects spiral around each other. Then they emit gravitational radiation after the two objects start to merge together. And then a black hole horizon form. And then there's the last bits of gravitational radiation emission, which is done due to the ringing down of the black hole horizon, which has this potato shape and rigging down towards this spherical shape. And then at the end of the evolution, because black holes have no hair, there exists a simple description of black hole just in terms of mass and angular momenta and charges, which says that all information that falls in is forgotten and the black hole stays stationary here. And this picture here of black hole evolution always ending up in the same place is very analogous to what an equilibrium state. An equilibrium state is that you take any system, a pot of water, you stir it, you shake it, you wait long enough, it's always going to end up into the same state, which is the state of equilibrium. So this is the reason why people have been trying to think about black hole as something analogous to equilibrium thermodynamical state. Now, just a little word about gravitational waves. This is the detail of the gravitational waveform you will get by the in-spiral form, then the merger, and then there's this universal last bit, which is the ringing down of black hole of emission. And here is the effect of a gravity wave on the ring of particle. As you know, it doesn't deform the shape of this ring, but not the area. Here. The main point about black hole merging is that every perturbation of black hole finally settles down to a static spherically symmetric configuration. As I said, this is analogous to the statement that any non-equilibrium thermodynamical system finally settles down to equilibrium configuration. Now the question is whether we could be more precise than that. Is it really true? If it's really true that this analogy works, then it means that somehow the ringing down of black hole should be the same as the process of relaxation to equilibrium. So this is my main point. If you want to have this thermodynamical analogy, you should go beyond equilibrium, and you should be able to show that somehow the mechanism of relaxation to equilibrium, which is essentially the mechanism of entropy production, the way systems relax to equilibrium, let's say if I stir a pot like that, the way it relaxes to equilibrium is that it's going to have some kind of internal entropy production, which is going to heat up a little bit the system and evacuate the system, and then which forces the system to go towards its equilibrium configuration. Okay, so essentially, if that's true, this analogy, what you have to demonstrate for it to be true is that you want to understand the mechanism of gravitational wave production, because this is what happens down in ringing down, as being equivalent to the mechanism of entropy production in a non-equilibrium system. And then also because when we do physics, let's say in thermodynamics, we do it locally. You know, I can steer my fridge here and it doesn't have to affect what happens there. We have to understand gravity quasi-locally. That is, without referring to the end of space or the end of time, as we usually do. Okay, so this is what somehow, this is the challenge behind developing a picture where gravity can be understood thermodynamically. So why do people believe that there's this analogy? And there's very little thermodynamic about it. It's mostly thermostatic about it. And essentially, I'm going to review what we know about the thermostatic of black hole. So black hole are objects which are at equilibrium, which are essentially review-bounding, Carter-King. They have a constant temperature. Now they satisfy a first law. If you change the parameter of the black hole, you see that there's a relation like that. The variation of mass and the variation of angular momenta is related to the variation of area times an object here, which is the surface acceleration. There's also an important law, which is the second law of thermodynamics, that the area of black holes always increase. But this is maybe due to the teleological nature of the definition of black hole horizons. And so this formula suggested people to identify this object A over 4gh bar as some kind of entropy, and then identify this object here, the object which is proportional to the surface acceleration as a temperature. This is where it started. The initial derivation is really about two different space-time which have different value of mass, angular momentum, and charge, and you compare how they relate to each other. There's been after a better derivation where you want to have, let's say, one space-time and have a process, because thermodynamics is not about comparing different systems, it's about comparing the change of a given system in time. So you like to know, to have this kind of law appearing as a process, and people have tried to do that, and there's some derivation, and this derivation works as long as you're in a context where you drop something into the black hole and you don't produce any gravitational wave, and then you wait long enough so that the things settle down in a particular manner, then you can also rederive this type of equality, but there are lots of assumptions that come into the game here. Okay, so now another element about the laws of black hole dynamics is this property due to Bekenstein, which is somehow this conjecture that there exists a generalized law, second law of thermodynamics, in the presence of black hole, you should ask the positivity of variations of the entropy of matter and the total area of black holes here. Now, something which I think is more deep and in some sense more robust than all these classical derivation is really this Unruh type of derivation, which is very generic. And then the Hawking derivation in the context of black hole. But Unruh is something absolutely very robust. Because it's due to entanglement of vacuous states or states in phi theory. And so this Unruh effect is essentially the statement that at the quantum level, a black hole radiates at the temperature, or any system which has an horizon, radiates at a temperature which is proportional to its radial acceleration. And the Unruh effect, it's even simpler. If you take an accelerated observer here, which will develop an horizon, then this accelerated observer has a radial acceleration. It has to accelerate away from its horizon. And this accelerated observer, if you put a detector on its world line, it would experience a thermal flux, which is exactly proportional to its acceleration. And the main property behind that is the fact that the vacuous state is let's say the Minkowski vacuous state is an entangled state between the left and right. And when you trace out the left degrees of freedom, you find a thermal state for the right degrees of freedom. If you use the Hamiltonian, which is really a uniform acceleration Hamiltonian for this boost. Okay, so all of this is very nice, but this is really a purely equilibrium condition, and somehow thermodynamics is about going out of equilibrium. It's about describing processes and changing time. I mean, thermodynamics was designed by somehow engineers to say what happens when you have a physical plant and you put heat and work and material and you get out something out of it. So you need to talk about changing time if you really want to do thermodynamics. And you need to go also to understand the mechanism of entropy production, which means you really need to understand what happens when you go out of equilibrium. Okay, so the question is, can we understand gravitational evolution as somehow some mechanism of entropy production happening in some kind of physical system? And then a deeper question, which is a completely open question in the field, is that we have a definition for this, the entropy of, let's say, a physical system without gravity. But there's no definition available to us to what is the notion of entropy when you take gravity into account. We don't know this fundamental object. There's there's conjectures, there's absolutely no definition. So one goal I have in mind would be that we need to be able, if we want to do gravitational physics, to have an understanding of what is the entropy of a system which is also containing gravitational degrees of freedom. This is one of the biggest open questions in, let's say, classical gravitational physics. And to see why it's such an important question, let's look at usually what we think time evolution is. So suppose we have a non-gravitational system, and let's see why gravity is so special with respect to time evolution. If we have an entropy, if we have a time evolution of a non-gravitational system, this is what it looks like, the second law of thermodynamics. You start from a state of low entropy. Let's say you put all the molecule of your gas on the corner, and then it's going to diffuse and occupy a bigger phase space. So this is a state of low entropy and high entropy. And if I show you a movie, you can tell which way is the proper way to pass the movie. This time or forward, what is forward in time and what is backward in time. Okay, and the prediction is that no matter what you do, you always end up in this state of equilibrium, when then there's no evolution. Okay, now there's a big fundamental puzzle, is that we have this data from WMAP, from Planck, and what these data show is that even the latest data of Planck are even confirming. People were expecting maybe non-Gaussianity, but what we find is that the early universe is the most perfect experimental example of a black body that we have. It's a state at total equilibrium. So the puzzle is the following: if the early universe is at equilibrium, why is there any evolution at all? Right? Because equilibrium means no evolution. And we see evolution, we are here, there are structures, there are planets, etc. So clearly there's something we fundamentally do not understand about the early universe, because we conclude from what we know that it's at equilibrium. Now there's this puzzle was raised the first time by Penrose. The way to understand the puzzle is to say, now suppose we look not at a thermodynamical system, but at a gravitational system. What does the time evolution look like? Well, in gravitational system, in fact, what I have to do is just reverse the arrow of time of the previous one. In gravitational system, I start from things which are, let's say, nearly homogeneous. And then gravity, which is this universally long-range attractive force, will start to gather and clump things together and make it look like that. And so the time evolution of gravitational system looks exactly the reverse of what happened in non-gravitational system. And the difference between this state here and this state here is that this state is a state of low gravity wave, and this state is a state of high gravity wave. And of course here, this is a state of low entropy for the matter, and this is a state of high entropy for the matter. So in some sense, if you want to reconcile these two things and have a second law of thermodynamics, you'll have to have a measure of the entropy related to gravitational wave production. There's no other way. And this is somehow one of the formula that one should be after if we want to understand the initial condition. So now can we understand, this suggests, it's a very suggestive picture, that we should be able to understand our gravity wave as entropy production. And then also we have to understand there's clearly something absolutely special about gravity, because any other form of matter or interacting in a non-gravitational way evolve in the way I was describing earlier, right? This is how matter evolves. But when you put gravity, this is what it does. So there's clearly something going on with gravity which is very different from other form of forces or interaction we have. So let's, okay, so the setup I want to do gravity, but I want to do gravity in a lab. So the setup is that I want to provide a quasi-local description of gravitational physics without having to refer to the end of space, like suppose it's asymptotically flat or the theta or whatever it is, or refer to the end of time. There is the notion of a black hole horizon, for instance, is a completely teleological notion. That is, you have to wait till the end of time before you know where your horizon is. There could be an horizon between us right now, but we have to wait 1 billion years before we know that there is. Okay, so it's not really a useful notion. It's not a very operational notion. So you would like, you know, the way we do physics is we do physics locally for a certain amount of time. So we would like to have a formulation of gravity that doesn't refer to this very interesting, you know, asymptotic notions, but is more quasi-local. So the setup is that for that you have to choose a screen, and what I call a gravitational screen. This gravitational screen would be, think about the boundary of this room. Okay, so it's a two-dimensional sphere, and this sphere is evolving in time with a certain time flow vector, and this is what I'm going to call the gravitational screen. So an ensemble of two spheres, let's say external and internal. Think for simplicity, there's just one external screen, and then you want to register what happens inside this screen. The time evolution of the screen is going to be now a time-like surface here. And you can think about the screen as equipped with a time flow as a proper definition of what you mean by a gravitational observer. Okay, so now, well, let me first give you the punchline. So the boundary of this, there's a domain, the inside of this room, the boundary of this domain is this screen. The punchline is the following, is that the gravitational physics of the region inside this screen is entirely encoded into its boundary, into physics of what happens in the boundary. And now, if you look at the equations of the boundary of the screen, it turns out that they're absolutely word for word equivalent to the non-equilibrium dynamics of a two-dimensional viscous bubbles in the presence of Newtonian gravity. So this is what I want to show, and in some sense this statement is and this is the punchline. So if you fall asleep, this is what I want to say here. This is essentially, this idea was first proposed as something called the membrane paradigm in some restricted context by Damour, Price, and Thorne. And you can think about what I'm going to say as a more precise and more thorough, implementation of this idea. So you can replace gravitational physics inside by something on the boundary, and the thing on the boundary, because it's an open system, it's going to be a viscous system. It's not going to be a Hamiltonian system.
This is gravity without matter.
What?
Gravity without matter.
No, matter will play a role. Matter will play the role that radiation, will play in a thermodynamical system. Let's say if you have nuclear radiation coming in, you have notion of heat, which is, yeah. So yeah, matter. No, matter will be okay too, in fact. So now, if you know a little bit about soft matter and the physics of interface, you know that an interface is really characterized by two physical quantities, which are very important. One is the notion of surface tension, and I'm going to explain what it means. I don't assume you know what surface tension is, but I'm sure I've heard the word. So one is the notion of surface tension, and the other one is the notion of internal energy. So in order for what I'm going to say to be true, I have to demonstrate to you that if you give any gravitational screen as naturally a notion of surface tension and a notion of internal energy attached to it. Okay, and then we'll see that once you understand what is the surface tension and what is the internal energy of this gravitational screen, the equations are essentially very natural equations. So why is that possible? The key element that makes gravity different, we already said that there's something different about gravity. Here I want to emphasize one point, is that the thing which is different about gravity from any other form of interaction is the fact that gravity is holographic, or locally holographic. So what do I mean by that? It goes back to essentially the principle of equivalence that says that we can always locally eliminate the gravitational field. So you cannot, the value of something at a point has really no physical meaning. Now, more precisely, let's look at some quantity which we usually use to do physics, which is the total energy of a system. So let me compute the total energy of a system. If I am in a non-gravitational setting, and I compute the total energy of a region, inside a boundary, it turns out that this total energy has two contributions, the bulk contribution and some boundary contribution. Usually we neglect that because the bulk contribution for large volume dominates. Okay. Now, in a gravitational setting, what's happening? As you all know, because of the invariance by diffeomorphism, the bulk energy always vanish. So for any gravitational system, the total energy, the bulk total energy is zero. There's absolutely no notion of energy here. So the energy in this room is entirely contained into the boundary of this room. And that's why maybe there's a possibility to describe everything from the point of view of the boundary, because energetically, the bulk is immaterial. Okay? This is what's really radically different from gravity. So this is in that sense that I would say gravity is holographic. And you can think of it very naively as some kind of energy screening. Anytime I shake something, I put some energy there, it turns out that the gravity energy degrees of freedom are always there, they permeate everything, and they always rearrange themselves in such a way that the total energy vanish. And so the usual notion of energy we use in a lab and we use in physics is an energy which is valid as long as you ignore gravitational energy. Another thing that this theorem says is that another property about gravity compared to other interactions is if you have electromagnetic interaction, you can create a Faraday cage and isolate yourself from the electromagnetic field. But in gravity, so this is a long-range force that you can just shield away, right? But in gravity it's not possible. There's no way you can create a gravitational Faraday cage and create a space in which there will be no gravity wave. If that was true, then you could be able to give a notion of what is the notion of bulk energy to things. And somehow these aspects, this universal attractive feature of gravity, the holographic nature of gravity and the impossibility of screening of gravity are related. This is and it would be nice, in fact, it would be nice, since there are gravity people here, to have really a proof of that, like a satisfactory proof that it's impossible to imagine a type of matter, try to construct, it's a very interesting exercise, to try to construct a gravity Faraday cage and see what it would entail. Right? Because if you were doing that, then you would prove that there's a notion of, you could define a notion of bulk energy, which I say is impossible, as in the nature of gravity. So the idea, but when I say there's no bulk energy, people, it's kind of puzzling because we use the notion of energy. This is, I feel it. So what we really means intuitively, and this is what I want to undo, is that in some sense, okay, the total energy vanish, but it's because maybe there's a way to separate this total energy into an energy of different nature, and this is what we do in thermodynamics. In thermodynamics, you know, for isolated system, the energy is always conserved, no matter what you do. Now, but what you do is that you say, well, look, there's two types of form of energy. One is called work, it's usable energy, and the other one is called heat, it's unusable energy. And the analogy is going to be very like this one. It's going to be like, in some sense, the usual form of energy that we use in matter is analogous in this thermodynamical energy to work, whereas the unusable notion of energy, gravitational wave, is analogous to heat. Okay, so that's kind of explain why you can have something which is always zero, but still you feel that there is something different about gravity versus usual form of energy. Okay, so let's go a bit more in detail into these things. So let's suppose I compute really the gravitational Hamiltonian, gravitational energy for this screen inside this room. I will find a purely boundary term, as I say. This boundary term has two components, one which is proportional to the mass, and the other one the angular momenta. I will talk only about the mass here for simplicity. So you find that the mass is given by a boundary term, which is the integral over the surface of square root of q times k, and k is the surface energy density, and it's essentially the total radial acceleration of the screen compared to a Lorentzian observer, the observer that are static with respect to a slice, and the free falling observer. Okay, so the total energy or gravitational energy contained in the region is given by the integral of the acceleration. This is a covariant generalization of the Gauss law, which we know in Newton, right? If we have a spherical body, the Newtonian acceleration is gm over r squared. If I integrate this object and divide by 4 pi g, I'm just getting the mass, okay? This formula, in fact, generalized for any system, and then when you specialize for different type of screen, you recover all these zillions of different formula that people have invented, but they're all the same formula, right? This formula agrees with the Komar mass formula. If you take T to be a Killing vector, it agrees with ADM mass formula if you take your screen to be at infinity. It agrees with Bondi energy if you take your screen to approach a null surface. It agrees with the Newtonian mass in the limit, and give me any other notion of mass, I will just bring it there. Okay, so there's just this one notion of mass. Of course, when people say there are different notions of mass, no, there's just different notion of observers. And then each observer has a different notion of mass, but that's not that, you know, that's a different notion of energy in some sense, which is not surprising if you think that even in relativistic context, you know, there's not a universal notion of energy. Okay. So now we look, there's some kind of thermodynamical relation, which are the smart relation that the mass is related to, let's say, the surface acceleration times the area plus the angular momentum, which is analogous of Gibbs-Duhem relation, which expresses the total internal energy of a system. And then you can look at the adiabatic variation, and up to factor 1/2, essentially you can see that the adiabatic variation of the mass, so when you have no gravity wave, and you demand no change in internal energy. I haven't yet defined the internal energy, but I'm going to. Then under this change, you find this type of relation, which is something like the first law, and you see that there's typically a term proportional to the variation of the area of the boundary. Okay, and the coefficient in front here is the radial acceleration of the screen. So you take the screen, it's an element of surface. Radial means that you have a radial direction there, and you can put out, you know, its acceleration in that radial direction. And this object, when you have a thermodynamical relation with the term proportion to delta A, this is what's by definition called a surface tension. Okay, the surface tension is, we're going to see, is the amount of energy you need to increase a system by a unit area. So sigma t, the radial acceleration for a general screen, is the surface tension. This is the appearance of one of the key parameters here. The surface tension for a screen is the radial acceleration. Okay, and we're going to see what it means to have a surface tension. What are the equations associated with surface tension? But before that, I want, now that we identified the surface tension, I want to say something about what is the internal energy here. In order to do that, let me try something I wanted to do for my daughter, which is 13, and I want to explain her Einstein equation. But the goal, she's entering high school, so I'm not allowed to use any equation. Okay, and I mean for her I'm going to make that into 30 slides. But let's say let me do it for you in 2 slides, and I can express exactly Einstein equation, not some approximation of Einstein, exactly Einstein equation in plain English, no formula. Okay, so to understand the internal energy, you have to capture the essence of what Einstein equation is. So what is Einstein equation without any words? So suppose now you take a plate, an array of freely falling observer that you dispose on a 2-dimensional disk, like that, plane. Okay, so this is my, and they are all freely falling, so they are at rest. So I just let my plane fall, like in the gravitational field. Okay, so if there is no gravitational field and you just let it go, nothing will happen, right? And if there's no gravitational field and no matter floating around, then this object will stay like that. Now, in order to formulate the Einstein equation, let's look at this plate on the side. Okay, so I look transversally on this plate, and I see this line of particles. Okay, so if nothing happened, nothing happened. Now let me do something. Let me take my laser pointer and shine some laser through it, or send a ball, or shout at it, or wave my hand, or send any form of energy, no matter what it is, right? Matter, light, sound, doesn't matter. Any form of energy is going to carry some momenta that's going to head towards these things. So now what can happen? Well, according to the famous physicist theorem that everything is linear to linear order, you know, if I send something through this object, it's going to deform. Okay, so how can a plane, how can a straight line deform to first order? It becomes a circle, right? So it means that after, the only thing that can happen after I send some things through it is that it's curved. You know, here I've curved it like that because gravity is attractive, but après it could be curved positively or negatively. Okay? So, and it's clear that at first order, the change of shape of this plane is always related to the change of the curvature of the curve, right? So if I take one transversal look here, the curvature is 1 over r, and suppose I take another transversal look, orthogonal transversal look, I'm going to get a change 1 over r prime. Okay, and once I've given you what is 1 over r, what is 1 over r prime, I've characterized completely what happened when I send any form of energy through my little plate of particles here. And by isotropy, it's clear that the change that is going to be characterizing by isotropy, you know, the physics should depend only on the sum of the two, so which is called the curvature. Okay, the curvature is the sum of the two curvature radius in these two directions. Okay, so here it's pure geometry. If I change the shape of something, it's going to change like that, at linear order. Okay, I'm doing nothing, it's just pure geometry here. Now, what is Einstein equation? Einstein equation is the following. It's the statement that the rate of change of curvature, this curvature I just defined, is proportional to the flow of transverse momenta. That's not that surprising, right? If you send more stuff, the transformation is going to be bigger. So it looks like I'm saying nothing. So the only place where I'm saying something is that I'm saying that now the rate of change is proportional to the flow of transverse momenta with the same negative coefficient, okay, for all inertial observer. So now if I observe my plate in one frame or in another frame, and I measure this coefficient, I will find always the same coefficient. This statement is equivalent to Einstein equation, and the fact that it's negative, that is the fact that it curves like that, is the statement that gravity is attractive. Okay, so this is Einstein equation in plain English. Let me show you now in 3 lines that this is absolutely equivalent to Einstein equation, not an approximation. Is that if you, and this is what I claim, I think a 14-year-old could understand. If you spend enough time, you know, you can draw things. I'm not sure I'm there yet, but you know, at least it satisfies my goal of saying, you know, it captured the essence of Einstein, of gravity. So let me put back equations. So rate of change, I'm saying rate of change of curvature is proportional to flow of transverse momenta, and I'm going to call this universal constant minus, because it's attractive, 8 pi g. Okay? So if I continue, now I'm more elaborate. Rate of change of curvature is d over dt of theta, my curvature. And now the flow of transverse momenta is always expressed by integral over S, my little surface, of TRT, the energy momentum tensor in the RT direction, where R is the radial one, right? TRT tells me what is the rate of change of momenta PR, by unit of time. So this is the mathematical expression of flow of transverse momenta. And now I'm saying this is true in any frame. So R and T can be boosted in any manner, and it's through any little screen. So it means that, okay, the only piece of mathematics which is non-trivial is to show that this object here is essentially GRT. Okay? So it means that if this equation can be written as integral over S of GRT equal integral over S of TRT. And since this is true in any frame, it says that GAB is proportional to L pi G T. Sorry, this one is minus GRT. Okay, so this is, you have to believe me there. So this equation is equivalent to this equation that GAB is 8 pi G TAB plus eventual, I cannot fix the cosmological constant with the definition. And here I'm using the fact that this is true for a screen. So this is equivalent to Einstein equation. Okay? And essentially what it says is that Einstein equation is an energy balance equation, right? Where it says on the right-hand side, this is something like the variation of E matter. What happened when, I put matter from one side to the other. And here it's the variation of what I'm going to call gravitation, internal energy of my screen. Okay, so the equation looks like delta E equal delta E matter, where the definition of internal energy now is uniquely fixed by these things. This is essentially the curvature divided by 8 pi G with a minus sign. Okay, so this is the two definitions. If you have a gravitational screen, you have a surface tension, which is a surface acceleration, and you have an internal energy, which is the curvature of the screen. The Einstein equation is just a balance equation that says that delta, this is the first law in some sense, says that delta of the internal energy is the variation, is the work force term. Okay, this is in a context where there's no gravity wave. Okay, this is elementary, but I think it's. So now let's go a bit deeper, because let's try, now that we have seen the basic elements of this construction, let's try to understand what is the dynamics of this system. And if I have this system, this screen and this boundary, which has surface tension and internal energy, it's going to have a density of mass, of angular momenta, and also of area. And you want to characterize the time evolution of M, of J, of A, how these things evolve. So you're looking for some kind of three equations, right? And in general, of course, M dot, G dot, and A dot is not zero, because this is an open system. So there's things flowing through my screen. If I send matter in, the mass is going to increase and the area is going to change. So in general, these objects are not conserved due to matter and gravity wave flowing in and out of the screen. Okay, so now the main thing is to show again that this time evolution of these objects, MGA, can be written entirely from a two-dimensional perspective. So now I want to erase the information about the bulk and show that it's equivalent to the non-equilibrium dynamics of a viscous bubble with Newtonian gravity. So in order to understand that, I have to spend some time explaining you what are viscous bubbles and what are the equations that govern them. And what is the physics of surface tension? Okay, so the key things about interface is surface tension, right? Surface tension is if you have a fluid, let's say, which is made of molecule, and there is some kind of long, short-range interaction, which is this van der Waals interaction. If you have a molecule which is on the boundary, it has less neighbors. So there's a deficit of attractive neighbor. There's a deficit of energy there. So it turns out that this object, they want to minimize the exposition they have to this boundary in order to minimize the energy, right? And then it means that when you're going to increase the surface of this object, you're going to increase the energy by an amount which is proportional to the area. And the definition of surface tension is that it's the energy that is supplied to the system to increase the area by 1 unit. Okay? And from the point of view of the system, you see, if you think that my system is two-dimensional, this term is exactly the same thing as minus PdV, where P is minus sigma. Okay, so this is the same thing as the work force, the usual work force term, but for a codimension 1 system. Okay, so it's not surprising that it's there. I'm saying that because in the original derivation, people were looking at it as TDS. They were finding this term very mysterious. I'm saying it's absolutely, if you have a boundary system, it's not mysterious to have sigma dA. Okay, and this surface tension is responsible for beautiful physics, the subphysics of droplets, bubbles, foam, evaporation, wetting phenomena, capillarity, adhesion, etc., etc., etc. And a big proponent of this physics is De Gennes, who has a beautiful book on that subject. And this is a guy using surface tension here to his advantage. So let's see what are the equations of surface tension. So this is the first equation of surface tension. So surface tension appear in 3 equations. I said there should be 3 gravity equations. In fact, there turns out to be 3 equations for surface tension. The first one is this one. Delta omega equals sigma dA. Okay, so work force term, which is analogous to minus PdV. Okay, the second equation is called Young-Laplace equation. It's an equation that I suppose it's an equation which is conveniently described for bubbles. So suppose I have a bubble that is an interface which now has some curvature here. What happens is that, you know, the pressure outside is going to be one thing, it's going to P out, and the pressure inside, when my surface is plane, the pressure outside and the pressure inside agree. Okay, at the plane interface, I have the same pressure, atmospheric pressure outside and inside in the fluid. But now, if my surface is curved, the pressure outside and inside, they do not agree, right? And there's a formula, which is Young-Laplace equation, which says what is the difference. So the difference in pressure between outside and inside is proportional to the curvature. Okay, with a negative proportionality coefficient. And the proportionality coefficient is again the surface tension. Okay, so that's another definition of surface tension as being this proportionality coefficient of the differential in pressure across curved surface here. And it says that if I have an object like that, which is positively curved, the pressure inside is higher than the pressure outside. And this is why you pay more for champagne than beer, right? Because you have smaller bubble and you have to get higher pressure inside. So it's not free. And essentially it says that the sigma theta r acts as some kind of pressure pushing the bubble inside. It's also responsible for plateau Rayleigh instability. So here, suppose, you know, if I have a little perturbation, I'm going to have a bulge and the crest here. On the bulge, the pressure inside the thing is higher, because it's curved like that. So it's going to push the bulge outside. But on the crest, the pressure, you know, in the air is higher. So it's going to put the crest inside. So it creates necessarily this, it's an unstable system. Right? It's going to cut the things, and if you drop a faucet, you'll see that very rapidly. Another nice application is capillarity adhesion. Suppose you take 2 plates and you create, so, you know, here I have a big circle that I don't draw, which is positively curved. But here I have a very small one, which is highly negatively curved. Which means what? Which means the pressure inside is negative now. It's smaller than the pressure outside. So it creates suction. And the suction can lift several kilos. You know, 2 little plates of glass, you can lift, you know, half or 2 if you're bigger enough. So it's pretty important. Okay, so this is capillarity adhesion. So this is Young-Laplace equation. This is the second equation. Okay, and the third equation, okay, now before the third equation, another instance where surface tension arises is in the wetting phenomena. If you put it's a liquid here on top of a solid, then you have the solid liquid surface tension and liquid gas surface tension. If the solid gas surface tension is stronger than the sum of the two, then the liquid wet. But if it's not, if the surface tension of the liquid is too high, then it creates droplet. And this is why you put, when you want to wash your floor, you put, you know, soap in it so that you get a bigger area with your, or this is why on a dirty floor, you know, water spread out less than on the clean floor. And this is what the little guy we saw use. So now when this inequality, when this object is smaller than the sum of the two, then there's an equilibrium angle condition, which is given by the Young-Dupré formula. And this is essentially what insects use as floatability device. Okay, it's also using capillarity rise. Here, maybe it's a nice thing if you have never seen it. Here it's curved negatively. Okay, so the thing is that here I have atmospheric pressure, here I have atmospheric pressure, here I have atmospheric pressure, but here I have a depression. And the depression compared to here, because it's positively viscous, so the depression is sucking up the fluid here. Anyway, so this is the beauty of surface tension. The last equation about surface tension is called Marangoni flow equation. It says if you have on a system a gradient of surface tension, this gradient is going to drive a flow on your interface or your bubble. And this is a picture of that. A beautiful example of that is something that, I mean, every drinkers of wine have witnessed. If you take a good crystal glass of wine, not plastic, you know, good crystal that create high surface tension, it means it's very wettable. So the wine, you know, naturally on the good glass, very clean glass, you have high surface tension, so you get total wettability. Okay, the wine wants to just wet the glass, so it goes like that. Now the problem is that not the problem, but what happens is that when I have a film like that, you know, it evaporates. So the wine evaporates from the film, which means that on top of the film I have water, and on the bottom I have wine. Okay, but the surface tension of water is higher than the surface tension of wine, which means that it draws a flow, which is a Marangoni flow, proportional to the gradient. So the Marangoni flow, it draws the flow towards high surface tension. And then it creates this kind of perpetual motion system where the wine is drawn up and creates this, you know, at some point gravity kicks in, creates these tears, and then it falls up and it continues to go. You know, on a good system with high alcoholic content and very clean crystal glass, it can be very spectacular. So that's another, this is Marangoni flow here. And it's also shown that in some sense, this will be the same thing as pi dot equal minus the gradient of P, one dimension lower. So P is again some kind of two-dimensional pressure negative. Okay, maybe I'm going to skip this one, which is also that, you know, the Young-Laplace equation has a dynamical version that the bubble can move, and there's an equation for it. Okay, what I was saying so far is for non-viscous fluid, right? Now, I want to talk about non-equilibrium, so I want to talk about viscosity or entropy production. So let me just say a little bit about the mechanism of entropy production in a general fluid. And then how it enters these equations, these three equations so from the previous, it should be clear. There are three equations associated with surface tension. Okay? There is Marangoni equation, okay? There is Young-Laplace equation, and there is the first law, okay? Okay, so what about entropy production? So now, if you look at the general fluid, one component fluid, it's characterized by two objects. One is called the viscous stress tensor, and here I denoted theta IB. It's the internal stress tensor is, you know, that responds to compression or deformation of the fluid. Okay, and the other one is called the rate of strain tensor. Is that if you have gradients in your velocity fluid, okay, you take derivative of the velocity on this direction that defines what's called a rate of strain tensor. So you have to think about the rate of strain is something which is a flux. Okay, it's Q dot. Okay, it characterizes the flux. And the viscous stress tensor is a force. Okay, so now the entropy, no matter what system you have, the entropy production at the classical level always have the same simple expression. That is, if S is the entropy and T is the temperature, Ts dot is always a product of flux times force. So this is called the flux and the entropic force. Okay, so here it's going to be the contraction of the rate of strain with the stress tensor. Now if I have a gradient of temperature, here beta is one over the temperature, the flux is called the heat flux, right? And the force is the gradient of the inverse temperature. So if I have a gradient of inverse temperature, it creates a force that moves things around. And if things move around, there's going to be an entropy production proportional to that. And the second law is essentially not this formula. This formula is a generic formula that follows from general conservation equation. the second law is essentially that these contractions are always positive. Okay, so this is one type of equation. Now the second type of equation that I have to give you is called the constituent equation. I have to tell you whether I'm talking about water or milk or honey or lava, okay? And they all satisfy the same, they produce entropy in all the same manner. What's different about them, it's some kind of phenomenological equation that says how is it that the viscous stress tensor is related to the strain tensor. Okay, so this is called this relation between force and flux determines what's called the constituent equation. And then, you know, when you do cooking, you're a master in changing the constituent equations of objects. This is what is chemistry too, but you know, you change things into a solid, into a liquid, into a jelly, etc. Okay, so now the things that people usually talk about a lot is called Newtonian fluids. In the Newtonian fluids, you just assume that the force is proportional with a constant coefficient to the flux. Okay, and this is the regime of hydrodynamics. But here I want to be more general. You know, hydrodynamics is only for specific Newtonian fluid. The gravity fluid are not generally, they are not necessarily Newtonian. Okay. So now, okay, now that I've introduced this notion of entropy production, we see that we have these two new objects, tendenters, which is the flux, the stress tensor, and the strain tensor. Now these objects enters, you know, all these three equations. Okay, these three conservation equations. So the conservation of momenta, which was Marangoni flow, there was the term gradient of sigma. Then there's an extra term proportional to the gradient of the viscous stress. You know, then there's the first law, the generalized first law, that, you know, you have the variation of internal energy, which I define. There's a term which is P dA. This is the term I talked about. And then there is a term here which looks like the entropy production, which is the contraction of stress and strain here. And there may be eventually heat flux. And also, if there is external matter, it could be external energy provided to the system. Okay? And then the last one is, I'm not going to, it's a generalization of dynamical Laplace equation, which is a generalization of Rayleigh, let's say, in the viscous context. But essentially here you recognize the surface tension term, the curvature, and the external pressure. So there's a viscous generalization for that. Okay. So now the main claim is that these three equations are exactly equivalent to the gravity equation projected on the screen. And if I take the gravity equations projected on the screen, I'm going, and I treat the screen as some kind of constraint surface, if you want, but it's a time-like surface, then there's going to be three types of equation I can write. Here, S denotes a normal vector to the screen, S for spatial. It's a spatial normal vector. And you can look at either the component GSA equal TSA, the component GSN equal TSN, or GSS equal TSS. This is going to be the Marangoni equation. This is going to be, this is conservation of momenta. This is conservation of energy on the screen. And this is the generalization of Young-Laplace equation. So these three equations are the same as the gravity equation. Let me focus maybe on the conservation of energy first. So it means that now I have a dictionary where I can identify any thermodynamical quantity with the gravitational one. And essentially, if we write the most general form of the first law, the general first law for a system with boundary is that the variation of internal energy has a form sigma delta A. So U is the internal energy, which is defined as the integral of the curvature. That was my definition. The surface tension is the radial acceleration. The matter flow that enters here is the integral of the energy momentum tensor. And then, okay, when you have a time vector, you have a notion of Newtonian potential, which enter the variation here, which is kind of surprise. And then there's an extra term, which is not sigma dA, which is the entropy production term. This is the term I was after. And this entropy production term is, maybe on the next slide, yes. So the entropy production term is not sigma dA. The entropy production term is the term that is the fluid entropy production term, is this integral of the stress tensor times the rate of strain tensor. And so what are these in gravity? In gravity, you know, because I have this two-dimensional surface embedded in space-time, there's two normal vectors. There's a radial normal vector and there's a time-like normal vector. So therefore, there are two notions of extrinsic curvature. One which is the time extrinsic curvature, which is going to be identified to the flow, to the flux, the rate of strain. That's not surprising. And the other one is the radial extrinsic curvature, theta r, which is essentially going in this combination to be proportional to the stress tensor. So the way somehow this relativistic system can manage to emulate a non-relativistic system is by unifying the concepts of force with the concept of flux, and saying that a force, so flux is a movement in time, and it's saying that a force is a movement in some imaginary radial direction, imaginary for the thermodynamical system. Okay, and once you say that, then you look at Newton's equations and they're really relativistic in some sense. So it shows that somehow these terms, the product of theta t, theta r, is really what measures the rate of gravitational waves in gravitational system. So it shows that in a precise manner, the notion of fluid entropy production is, you know, how we would measure the amount of gravitational wave crossing a system. So in this analogy. And then this dictionary here can be extended to all elements of thermodynamics. So I'm giving you some example. I repeat here, this is the thermo side and the gravity side. So the notion of internal pressure is the radial acceleration or surface tension. The external pressure variation is the radial pressure, PSS, the radial component of the stress tensor. The internal energy, we saw, is the radial expansion. The external entropy rate production, so the one you would have in a nuclear reactor, is just the momentum, the energy flux. And the thing which is maybe less obvious is that the rate of strain tensor is the temporal extrinsic curvature. Okay? And then the viscous stress is the radial extrinsic curvature. And then also you can go down that the momenta of the fluid has a momenta, and this momenta is corresponds to what's called the normal form. For the specialists, they recognize this object. That because I have two normals, I can take the derivative of the normal in the tangent direction and project it into the radial direction, and it gives me an object which is a one form, but it turns out to be equivalent to the momenta. And then etc. And then the big challenge is to go beyond and to talk about velocity and constituent equation. But I'm going to stop here because it's pretty dense already. So essentially what I've wanted to talk about here is that we have seen that due to its holographic nature, gravity in a box can be equivalently described in terms of its boundary, which I call the gravitational screen. And a gravitational screen generally processes a surface tension and an internal energy. And from the screen point of view, Einstein's laws are rephrased as fundamental laws of thermodynamics, plus a fundamental law of evolution of somehow the expansion of the screen, you know, which is this Rayleigh-Laplace equation, which is a generalization of Young-Laplace equation. And that's what I say here, that this evolution, what I call the Hawking entropy rate. I mean, in this gravity game, there's some kind of two notion of entropy. There's the notion that, let's say, Hawking proposed that the entropy should be the area. And here, there's another notion that I propose, which is that there is the entropy of this fluid system, okay, which has its own entropy. And the question would be, are they the same? And they are not exactly the same. Near equilibrium, they're going to agree, but in general, they are not. So what I call the Hawking entropy is essentially the area, and the rate of expansion of the area is controlled by this dynamic called Laplace equation. And of course the proposal behind is that I think this brings new lights on the nature of gravity, a new point of view on non-equilibrium physics and new questions. As I said, there's two notions of entropy, the usual Hawking notion of entropy as area, but the viscous fluid notion here, which I think is more justified, because it appears in the right way in all the equations. And then what can we say about their relation in non-equilibrium regime? You know, the thing, okay, this is a more general questions about thermodynamics, that people are still looking for some kind of generalized principle that would determine, we know that S dot is positive, but that's not a law of physics. A law of physics will be S dot dot equal, right? What is the law that determines how a system relaxes to equilibrium? Okay, and in certain systems you can devise this object. In general, it's not known. Here, it's related to this law that says how does a gravitational system relax to its black hole equilibrium state. And people, what we do today is we do it numerically by putting asymptotic boundary condition, and we try to follow what's happening. And but there's no good understanding of what's going on besides numerics. Or perturbative, quasi-normal modes perturbation. And then, okay, essentially, maybe if this analogy really survives, we could use it to go deeper in the same way that somehow the nature of fundamental matter was first discovered by Einstein through a fluctuation dissipation theorem. So here, if I claim that gravity is naturally dissipative, maybe there's a similar reasoning that could apply in the end. And then, is it useful? Can I use this analogy to tell people what they are? This is a challenge to really show that your analogy is useful. So here it's kind of a reformulation, but being useful means that you could be able to tell people doing numerical evolution that their ringing down of black hole is exactly the same thing as relaxation of agitation in a fluid. Okay, and I think that's all.
Maybe I'll just say both questions. So the first thing is, what about time? I mean, in the thermodynamical system, I have fixed external time. So is it when you choose the screen, are you choosing a preferred time? That's the first question. And the second one, well, I mean, given that you have this analogy here, would it then be possible, rather than run some numerical simulations of this ring down of black holes, could you find a real life fluid system where instead of simulating it on a computer, you could simulate it in the lab?
Let me answer the second one. So this is the goal. Part of showing that this program is successful is ending up there. I would agree. So that you could use soft matter physics type of experiment to do real simulation. Yes, that's. I cannot do that at this stage. I cannot demonstrate that at this stage, but this is really where I want to go. I want to understand the processes of ringing down, which is not really understood in gravity properly. And it's related to your first question. So the first question, yeah, here what I describe is the equations when I set up the screen. Okay, that is if you, okay, so I have my screen, and as you say, I set up a time evolution for it. Okay, so let's say, if my screen is a point and my space-time is like that, I kind of choose a way to embed it somewhere. Okay, so once I have that, I can write this analogy. Now, you want to go beyond that. You want to say, okay, well, but this time, you want to make this time become an external thing. So you can ask, what does it mean to change my notion of time? Yeah. So from the point of view of the screen, if you take a different time evolution, what you're changing is the constitutive equation. So let's say if that guy, if I take a screen which is nearly null, then it's going to be a Newtonian. So it's going to be that the stress tensor is proportional to the strain tensor. So this is Newtonian regime, let's say. So it's like water, the things behave like water. But now, in here, if I take something which is hardly time-like and wiggles in a specific way, I'm going to have a fluid which is maybe more like mud. It has a constitutive equation with memory. So what this picture allows you to do is so the choice of time amounts to what we do in thermodynamics. So in thermodynamics, time is fixed, but we fix also something. You decide to work with water, or you decide to work with whatever material you're deciding to work. And this amounts to a choice of placing your screen in space-time. Okay? So this is the thing I'm now developing, is to understand really how to do this mapping. So there's an interesting mapping that there's arbitrariness in thermodynamics. When you decide to work with butter or water, you have your one component system. Here, the arbitrariness of choice of time is the arbitrariness of choice of material. Okay? So does that answer your question?
I have to think about it, yeah.
Okay. No, I know it's a kind of a and Yeah, I mean, there's a deeper answer maybe behind that.
Are you proposing that gravity is not fundamental? Just a fact.
No, I'm not proposing anything here. I want to know what gravity is. So you know, I think here I'm only halfway, mostly because of this problem of time. I'm only halfway through proposing that gravity could be equivalently. So the first thing is that it's a conjecture. I'm talking about classical gravity. Is it true that classical gravity can be equivalently reformulated as non-equilibrium thermodynamics? And if that's true, then I could do the experiment she wants. A part of water would simulate what, you know, more efficiently what a supercomputer can do. Okay, that's the first thing. And for that, I have to tell you a bit more about the constitutive equation versus the placement of the screen, okay, which I haven't discussed today. So if I have a good understanding of the constitutive equation versus the placement of the screen, what I'm doing is I'm treating my gravitational system as an autonomous system for the boundary things, and then, you know, I can completely forget about gravity. Okay, suppose I can do that. So it's only, you know, there's two steps in the process. One is the general equations. The second one is the constitutive equation. So suppose I have done that, then I don't know, then it opens new ways, I think. This is why I'm interested in it. It opens new ways maybe to think about what is entropy of gravitational system, which means that, you know, if you start to know what entropy is in gravitational system, you might have some clues about what are the degrees of freedom. What I'm saying here is that this idea that entropy is area, okay, it's kind of, it's nice, but it's way too naive, okay? It's going to be more, you need more information than that. So you want to have this extra information. And then, yeah, it might, you know, I'm not saying it's not fundamental, but it might lead to another way to get a constituent picture, like fluctuation dissipation. Right? If you have a system which is like thermodynamics, then, you know, if the question is, this is a classical analogy between classical GR, okay, this is a classical GR and non-equilibrium thermo. Okay, so now we know that there's two deformations of these things. I can deform classical GR into quantum GR, okay, or I can deform non-equilibrium thermo into statistical mechanics, right? So, you know, the question, so suppose you show the equivalence here, then the question is that, okay, is it true in some way that the classical equivalence, you know, survive at the quantum level? Or you could, you know, study that and say is what it is. I mean, I don't think it means that you should prefer one to the other. Maybe ultimately the picture I have is that I should have something like that. And this equality is something like Wick rotation. I mean, I don't know. But it clearly gives a completely different way of thinking about quantum gravity. Or let's say, thinking about a constituent picture of gravity. Yes. And as you know, this is what I'm really after all the time. Yes?
You mentioned Newtonian gravity, right?
Yeah.
So do you really mean Newtonian gravity on a curved space? Is that what you really mean? Generalization.
Yeah, some kind of generalization. I mean, there's this scalar field here, which is a scalar. It's a scalar potential, and it couples to the internal energy. So the mass is internal energy. So I call it, yeah, Newtonian.
Just write down all the equations to put in the
Exactly. Yeah. With a preferred time here. And this is a term I would. All the other terms I would kind of expect them. This one is kind of bizarre. It just comes from the fact that, I mean, in Newtonian physics you have a fixed normalization of the time, whereas here you can rescale it, and this shows in your thermodynamical equation as this Newtonian potential, this rescaling. So it's there. I don't know. It's just there. You have to do it. Yes?
Maybe I want to also to Kirill's question. So I think Kirill asked, is it a partial analogy or is it a complete analogy? And then you draw the right-hand side and say, well, I mean, what I kind of don't understand, let's say you have this analogy and now you want to say, okay, can I learn something to quantize the system?
Yeah.
And I mean, do I get that wrong, or we don't have a quantum description of fluid dynamics.
No, but no. That's what I'm saying here. So, let's say, suppose I've proven, it's more than, I've proven a dynamical equivalence at the classical level between GR and non-equilibrium thermo. Now, let me think about quantum as a deformation. I'm thinking in terms of, I don't know, I'm taking my mathematician hat here. You know, I think of quantum mechanics as a deformation, in the sense there's a parameter, we can call it h bar, but it's a deformation parameter of my observable algebra, my observation, such that when h bar equal to 0, I recover classical physics. Okay, so quantum gravity, whatever it is, we don't know, nobody knows, it's a deformation of classical physics, of classical GR. Okay, now let me go on the other side. And here it's a deformation with h bar, okay? Now, on the other side, in non-equilibrium thermo, what's interesting is that there's also a notion of deformation of non-equilibrium thermo, which I call statistical mechanics, where now you put the Boltzmann constant into play. So kappa plays the role of a deformation parameter, right? And in statistical mechanics, you are going to have non-equilibrium thermo plus higher order correction, which are going to be proportional to k, in the same way that you can expand your quantum gravity expansion. So the question is that, you know, I could either deform that object or deform that object using either quantum or statistical mechanics. I'm not saying I should deform this object with quantum, okay? I'm just saying there's two deformation. And now you're asking me, Kirill is asking me, well, does that mean that this guy is better than this guy, or that this guy is better than this guy? I don't know. I'm saying, for me, first, if there's two deformation, I find it amazing. But I find another possibility even more amazing, is that in fact these two deformations are the same, right? They are just, you know, there is a correspondence between these two, which means that extend this equivalence. So this is really what I'm after. And so then nobody is more, you know, you could, once you have this equivalence, you can decide to say, well, it's like that or it's like that. It doesn't matter if it's the same thing. So, you know, then it's a question. I mean, here I'm really going ahead of myself. There's a series of questions. Can you first prove that? And I say, I think I would say yes, I can bet. But you still have to let me work a little bit, okay? Then, you know, can I deform that? I say, I don't know. You know, can I deform that? Maybe better. So maybe here what we know is that once we are there, maybe it's easier to get some kind of deformation. And then, you know, is there some equivalence? It might be that there is, you know, if there's a classical equivalence with two possible deformations. It's so hard to deform gravity with the quantum parameter that maybe there's only one way to do it. I don't know. Or they are orthogonal. I mean, I'm totally agnostic. I don't want to bet. Does that answer?
Just one last question. I think you have to answer but now.
Yeah.
What about the degrees of freedom? If the two systems are dynamically equivalent, they have to have the same.
Yeah, this is why I worry about what is entropy. So the whole thing about the degrees of freedom is what is the entropy of a gravitational system. It all boils down to that. If you want to prove a thermodynamical picture, let's say, which I want to push for, you have to tell me what is the entropy of a gravitational system, right? Once you have that, it means there's degrees of freedom, and this entropy has, at the same time, you see, if I can devise the notion of entropy for gravitational system, it means that it has a statistical interpretation from this side, but it means it has also a geometrical interpretation, because it's the entropy associated with GR system. And that's the challenge, right? So another way to get where I want is somebody that comes and tell me the entropy of a gravitational system is. That would give me the answer. That would give me the fundamental clue. So when people talk about fundamental degrees of freedom, they talk, well, I have in my head a formula for the entropy of a gravitational system. But then when you probe them and ask them, okay, give it to me, they say, shh, no, not to you, not now. Or you know, they don't have it. Nobody has it, right? And so to prove this analogy to be right, you need to formulate your conjecture about what is the entropy. Yeah.